Hello everyone, welcome to Chapter 5, Integration, and we focus on definite integral substitution, and we'll use the substitution technique to handle definite integrals. And what is true here is also true for indefinite integrals, so we'll probably look at a couple of problems there from indefinite. But we'll go into the substitution method and see how we go about it. Here is the definition. If g prime is continuous on the interval ab and f is continuous on the range of g of x equals u, then integral a to b f of g of x, composition, times g prime of x dx is integral g of a to g of b f of u du. Okay. I know it sounds confusing. To put it simply, remember that we cannot always find integration for some functions to be easy, because the way they're set up could be challenging for us to use the known techniques of chain rule, power rule, and all that. Now, for that reason, we use the substitution method, which is nothing but chain rule backwards. Okay, so substitution method is chain rule backwards. And that's why this definition kind of looks complicated. But I will try to show it to you through an example how we use U substitution. We call it U substitution because you use the letter U to substitute for a difficult expression and use that as a way to deal with the integration. So we're using chain rule backwards. Okay. And if you recall, chain rule was, if I wanted to do dy over dx, I had to first do dy over du. We use the u, isn't it? Times du over dx. We use the u to get from y to the x. So same idea here. We'll be using the u to be able to integrate it. So let's start off with the first example. So I'm going to use indefinite integral here to drive home the idea, and then we'll look at definite integrals. So that's basically our topic. Yeah. Now, clearly, the power 5 here makes it difficult for us to distribute. I mean, to expand first and distribute it. You could do it. It's very painful to do that. Expansion. Now, because it's 5, it is doable to some extent, although it's tedious. Imagine if the power was 10, right? That's going to be even more challenging. Almost impossible for us. Computationally, it's going to be a nightmare. Therefore, for these kind of complex expressions, we want to use the U substitution to break it up. Okay. So the whole idea is we want to choose U to be one of these factors, right? We have two of these. So one of these factors should be the U, so that when you do the du over dx, you'll get the other factor. Right? That's the whole idea. So that I could substitute the entire thing for the u in terms of u. So let's say, so this is trial and error. So I'm going to try this, okay, for 3x squared plus 1. If I did du, remember you're doing the differential, right? So du over dx is what you do, but you'll throw the dx on the other side. So I'm just going to show you the du. That's going to be 6x dx. If you come back here, there is nothing there that helps us to deal with the 6x dx, because you have this expression that you rewrite, that you have to then try substituting u for the other one. You don't need to put the power 5, because u power 5 will be this thing power 5. So du will be 3x squared plus 1. And there's an over dx that comes to the right. And look at that. Now this thing works because you can find, you can substitute u for one of the factors and its derivative gives you the other factor. So all I have to do is come back and do integral. That's going to be u power 5. And this whole thing, 3x squared plus 1 with the dx, becomes my du. Look at that. How easy is that? So then I can just use the u as my new variable, and then that's going to be u power 5 plus 1 over 5 plus 1 plus c, because this is indefinite integral. That's u power 6 over 6 plus c, but we know what u is, so you have to back substitute for u. Remember, this is like a crutch, right? It helps you to get past that issue. So once you have used it, you have benefited from it, you go back to the original expression, which was x cubed plus x, that was our u, power 6 over 6 plus c. And that is how it is so convenient to use the substitution rule. And this rule will help us to handle complex expressions, to help us to integrate, and mostly it will work. Okay? And as we move into, say, calculus 2 and 3 and so on, we'll have additional techniques on top of the u substitution that you can use to navigate through the problem. Let's do another one. I say find integral secant squared 5x plus 1 times 5 dx. Okay. Now if the question itself had a u, of course use some other letter, use w or something else to substitute, but in general we call it the u substitution. So the problem here is not secant itself. Secant squared something has its has a formula, so we can use that. The challenge here is this expression here, 5x plus 1. So that is the one I want to substitute for. So that du will be 5 dx. It's all lining up nicely. I mean, of course, I'm giving you examples that are nice for substitution, just to drive home the point in the beginning, and then we'll look at some other types too. Alright, so integral of secant squared x is tan x. In this case it's u, so this is going to be tan u plus the c, and back substitute for u, that's going to be tan 5x plus 1 plus c, and that's your answer. Alright, now what if it didn't match up exactly? So here comes another example for us. Integral cosine 7 theta plus 3 d theta. Once again, we know there is a formula for integral cosine x, but this is the problematic piece, so we say let u be equal to 7 theta plus 3. So du will be 7 d theta. So let's come over here and say cos times. There is no 7 times d theta, there's only a d theta. So you're going to come back here and say du over 7. If I divide both sides by 7, I'll get a d theta. Right? So my d theta can be substituted as du over 7. This is not a problem at all because you can pull out the constant. So I can put it as 1 over 7. Remember, 7 is in the denominator, so when you pull it out, it's going to be 1 over 7. Integral cosine u du. And you can go about your business because you don't have any complication coming out of dividing by 7. And integral of cosine u is sine u plus c. And of course, back substitute. U was 7 theta plus 3 plus c. And that's your answer. Evaluate. Integral x times square root of 2x plus 1 dx. Wow. Okay, here again the problem is that the radical has this huge expression, right? If it was just say x, you can do square root of x as x power half, but here you have a binomial, an expression there, so you really can't deal with it easily. So we're going to use the u substitution for that, 2x plus 1. Du will be 2, and you're taking the derivative, so that's going to be dx, right? Now I can look at the expression here already and see that there is no 2 times dx, which means x. So this implies integral, oh, look at this, now I have x. So I cannot use the x as it is because I have to write it in terms of u. But thankfully, I can rewrite this as well in terms of x. So that's going to be u minus 1 over 2 will be x. Solve for x, basically. Okay. And so we're doing two things here. So I have an x where I have to rewrite it in terms of u. So go back to the u substitution and rewrite or solve for x. So I get u minus 1 over 2 times square root of 2x plus 1, which was our u, times dx is du over 2. You see that? That's a lot of work there. But it's not really bad, as it seems. The 2 and the 2 in the denominator will multiply to give us 1 over 4 integral u minus 1 u power half du. Right? That looks neat. And we know that this is completely doable because all I have to do is u times u power half, distribute the u power half, minus u power half du. We did a very similar problem previously. I think we used a t in that problem. So 1 plus half, you use the exponent rule where you add the powers. So 1 plus half is 3 over 2. So it's u power 3 over 2 minus u power half du. Alright, so that means we have 3 over 2 plus 1 will be 5 over 2 over 5 over 2 minus half plus 1 is 3 over 2 over 3 over 2 plus c. Okay, this plus c is so convenient. Okay, when you have the definite integral, you have to plug in the numbers, the top integral minus the bottom integral. It will be a little more challenging there. Alright, so we have 1 over 4, 2 over 5. U can be replaced by the 2x plus 1. Okay, you can leave the answer like this, or a simplified version would be to pull out or factor out this 2, right? You have 2 and 2, so the 2 comes out. That 2 over 4 will give you a half. You can have it as half times 1 over 5, 2x plus 1 power 5 over 2 minus 1 over 3, 2x plus 1, 3 over 2 plus c. Or you can write them as separate steps. Separate fractions, I mean. So that's going to be 2x plus 1 power 5 over 2 over 10 minus 2x plus 1 power 3 over 2 over 6, multiply them out, and then plus c. So it's either this or that. Okay. Now when you use trig functions, sometimes you'll have to use a trig identity before you use the u substitution and so on. Okay. So I'll show you one with a trig identity. Look at this. Now in this case, our challenge, one of the challenges is that you have this sine 2x, right? That's like a double angle there. It is a double angle. Then you have 1 minus 2 sine squared x. So you always want to hold on to your trig identity sheet in calculus. You never know when you'll have a trig problem. So you do have the sheet. If you have the sheet in front of you, you can scan through the identities, and you're looking for identity where you can simplify a square. So look for power reducing identity, and there if you go through it, you'll see that there are variations for cosine 2x. So you can see it as power reducing, or you could see it as a double angle, which in turn gives you the square version of it on the other side. So it just depends on where your trig identity. I can say this. This 1 minus 2 sine squared x, okay, can be directly given to you. It depends on which version you're looking at. If you are, you can view one of the sheets that I have shared in Canvas. But you can also check out something on Google as well, and you'll find that, or in fact you could go back to our ebook and see it there, because that's the best place to look for. If I were to kind of derive this, I know one is sine squared x plus cosine squared x, right? That's a Pythagorean identity, minus 2 sine squared x. So this sine squared x minus 2 sine squared x will be a minus sine squared x. So that's cosine squared x minus sine squared x. I combine the like terms, right? And this gives us cosine 2x. So if you didn't find it directly, say cosine 2x was just given to be cosine squared x minus sine squared x, we can still derive from here all the way down to cosine 2x. So what this allows us to do is rewrite this given question. Let me write the question first. As this 1 minus 2 sine squared x is now cosine 2x sine 2x dx. Now if you go to another trig identity, okay, in fact some of these identities are derived from one another, that you could be looking at two different looking identities but that they came from the same one. For instance, here I am thinking of the sine double angle for sine. Sine 2x is 2 sine x cosine x, right? But here I have sine 2x cosine 2x. That means all I have to do is double this so that I get 2 sine 2x cosine 2x. We know that, right? That's something you learned in trig. So if I want sine 6x, it's going to be 2 sine 3x cosine 3x. So each time it's double the angle on the other side. Or you can, if you're seeing it from this side, then it's half the angle. So that is something you can use, so that this implies if I divide both sides by 2, I get sine 2x cosine 2x. Okay, this is one version. The other version is you can go to product to sum rule. Okay, or you could also see it the other way, sum to product rule, whichever version you're seeing. And you could use the same thing, product to sum rule, to arrive at the same information. So they are two separate formulas, but they are actually pointing to the same information. So it's your call. I choose to do it this way. And so I'll come back and substitute this as sine 4x over 2 dx. See how simplified it is now? It is just the sine 4x dx. We have a formula for integral sine x, not for sine 4x. And therefore, this is a good time for me to substitute. So this is where I'm doing the actual substitution, the U substitution. The previous substitution was the trig substitution. It was the trig version, not the calculus technique that we're using for substitution. Anyways, U equals 4x is my substitution. So du will be 4 dx. But I know there is only a dx, so du over 4 will be dx. So I come back here, say okay, I have half integral sine u times du over 4. I'll bring that 4 outside to this 2, so I get 1 over 8 integral sine u du. Now from our integration formula, we know integral sine u is negative cosine u. So that's 1 over 8 times negative cosine u plus c. That's negative 1 over 8 cosine u, but we know u is 4x plus c. Okay. Now again, I strongly remind you not to go beyond the answer. Please don't try to do this 4 and the 8. You can't do that because the 4x is an angle that's contained in the cosine, that's in the argument. It is not free for you to cross cancel with the 8. That 1 over 8, negative 1 over 8 is a constant, but 4x is an angle in cosine. So you can't really cancel them, so don't do all that. But this is what you're able to do in using the trig identity. Alright? And there are other places, there are other problems where you'll use the substitution. whether it's in the numerator or denominator, and then you can get from there. So I'll just show you one of them. I'm showing it to you in the indefinite integral only because I want you to be familiar with the idea, so that when we do the definite integral, you're focusing a little more on the substitution of the limits, not the u substitution itself, right? So I hope that portion will move quickly for us, because we are focusing just on the u substitution technique here. So we had something like this. Again, it looks complex for two reasons. One is that you have that cube root, and that is sitting in the denominator. But no problem, that is problematic. Then that's what we want to see if we can substitute. So z squared plus 1 du will be 2z dz. Wonderful. That gives us our numerator. So then I substitute now. So I get u, oops, not u, it's du over cube root of u, right? The whole thing, the radicand is now our u. It still looks complicated, but it's really not, because you can rewrite the cube root as a power. So that's going to be 1 over 3, isn't it? And this is sitting in the denominator, which means you can move it up to the numerator by changing the sign of the power, right? Negative exponent rule allows you to switch over. Flip the base, change the sign is the technique we use. Alright, so that's going to be negative 1 over 3 plus 1 over negative 1 over 3 plus 1 plus c. And that will be 2 over 3, u power 2 over 3 over 2 over 3 plus c. That becomes 3 over 2, the denominator flips, right? Then it's u power 2 over 3 instead of u. Now you can substitute for it as z squared plus 1 power 2 over 3 plus c. And that's our answer here. Alright, we are pretty much prepared to go for definite integrals. Evaluate integral negative 1 to 1 3x squared square root of x cubed plus 1 dx. Okay, we know how to do the substitution. You were already thinking of using x cubed plus 1 as u and use the u substitution. So we know that substitution part. What I'm going to do is show you two methods of using the integration, the limits of integration. Okay? So method 1 is this. So you're free to choose whichever method you lean towards, but it's good for you to be familiar with both methods. Okay, in method 1, well, both methods begin alike, so we do the u substitution first. So du is 3x squared dx. You can see the 3x squared in the front and the dx in the back, but they're all being multiplied, so you can kind of move them all together so that you can see it as du. So all that is good. Now what happens is these limits of integration, as you see in the problem, it was related to this x, right? Limits are for x. Okay, that is in a given problem. But when you do the u substitution, you really have to remember to adjust those limits for the u, because you're now using the u. Okay, and if that is the case, so that's what we do in method 1. In method 1, we convert everything to u so that we don't have to back substitute for u in the end, because everything is now switched to u. Okay, in method 2, we'll back substitute for the u like we did in the indefinite integral, and therefore we will not be replacing or changing these limits of integration. Okay, so in method 1, we're changing the limits of integration. That is what's happening in this method. That means I now have to plug in when x is equal to negative 1, it implies u is, plug in for x as negative 1 in u. So negative 1 the whole cube plus 1, which is negative 1 plus 1, right? Which is 0. And then The other limit is 1. So when x is 1, 1 cubed plus 1, it is 1 plus 1, 2. So the limits of integration, okay, will now become, instead of negative 1 to 1, it becomes 0 to 2. 0 to 2. And 3x squared dx, I'm going to move it there. So I'm first substituting for square root of this. So square root of u du. So I'm going to point out to you and say these are limits for u. The benefit of this method is that you don't have to go back to replace the u with the x. And so 0 to 2 u power half du, which is u power half plus 1, which is 3 over 2 over 3 over 2. You don't do the plus c, instead you'll have to apply the new limits 0 to 2. Okay? This is going to be 2 over 3, that's a constant, so forget about that, meaning keep it outside. And do the top substitution, 2 power 3 over 2 minus the bottom limit, which is 2 over 3. Square root of 2 cubed, right? Basically that's what it is. You can see that if you did it sideways, okay, square root of 2 the whole cube, that's what it means, which means root 2, root 2, root 2. These two will become 2, right? So it's 2 root 2. So it's basically 2 root 2. And with this 2 outside, this becomes 4 root 2 over 3. That will be the answer from method 1, where you switched your limits for the u. You moved from x all the way to u and completely used u throughout the rest of the problem. Now let's go to method 2. Method 2 says that we will replace u with x in the end, which means we will not adjust any of the limits. So same story, let u be equal to x cubed plus 1, du is 3x squared dx. Because our problem is kind of far away now, I'll just rewrite the question here. Now what I'm going to do is, in method 2, put it down here, I am going to keep the limit from negative 1 to 1. I will be changing all of these to u. Okay, so let's quickly remind ourselves. Limits are for x, not u. So even though you have the u in the problem, you're being extra cautious to understand that you're not ready or you're not supposed to apply these limits until you have replaced or back substituted for u. So that's going to be u power half plus 1, which is 3 over 2 over 3 over 2, negative 1 to 1. Again, let me remind you. Do not substitute until you have replaced u with x. Okay. So what I do is I write the 2 over 3, okay, and I replace the u, which was x cubed plus 1, right? I replace the u, and then I will apply the limit from negative 1 to 1. Okay. So let's say now apply the limits. So now we are good because it's all back in x. What I like about this method is we didn't have to do that extra calculation for the limits, and in some sense, you know, less calculation means less ways to go wrong or less places to go wrong. And therefore, I like this just because it reduces the calculation. The only thing is to remember to bring it all back to x before you plug in for the limits. So this constant can be out here, and what I'm going to do is 1 cubed plus 1 power 3 over 2 minus negative 1 cubed plus 1 power 3 over 2 bring in all those extra brackets there because you do have the minus in the formula, right? Top minus the bottom, and there is a -1 to substitute. Watch out for that. That's going to be 2 power 3 over 2 minus, this is going to be -1 plus 1, so 0 power 3 over 2. 2 over 3 times 2 power 3 over 2. There I showed you 2 power 3 over 2 as 2 root 2. Here I want to show a slightly different algebraic technique. It's not new. You've done this before. They both have the same base 2, so you can add the powers. So 1 plus 3 over 2 will be 5 over 2, right? So you get 2 power 5 over 2 all over 3. So you can leave it like this, but it doesn't match with the answer back here, right? You want them to have the same answer, 4 root 2 over 3. That's why this way of expanding it is a lot easier, better, I would say, compared to the exponent method. But say you were doing the exponent method, it's still not bad, because what you're doing here is 2 power 5 over 2 is root 2 power 5, isn't it? So root 2, root 2, root 2, root 2, and root 2. These two will be a 2, these two will be a 2, and then that's a root 2. That's how you get the 4 root 2. So the same thing replaces as 4 root 2 over 3. That's the same answer as method 1. So method 1 and method 2 should give you the same answer. And it's all the question of how you do it. Quick recap. In method 1, we transform the integral and evaluate this transformed integral with the transformed limits, right? You switched everything from x to the u. In method 2, you transform the integral, but then you integrate, and then you change back from u to x and use the original x limits. Okay? So I'll try my best to switch between the methods and to kind of give you a variety. But I personally will lean towards method 2. So let's check out some of these examples here. Find integral pi over 4 to pi over 2, cotangent theta, cosecant squared theta, d theta. Okay, that's given to us. Again, you want to go back to the formula and see which one gives you the integral formula. So if you go back, you'll see that if you chose cosecant squared theta as your u, if you did the du, you'll have to do the chain rule. So 2 cosecant theta times the derivative of cosecant. So that is going to be problematic. It's going to lead us away from what we need because it gives us an extra cosecant. We don't want that. So go for cotangent theta, and there you know that derivative of cotangent is actually negative cosecant squared theta d theta. The negative is not a problem, right? We can divide both sides by the negative, which means du over -1 is cosecant squared theta d theta. So all good. So I'm using method 2. U du over -1, which is basically negative integral pi over 4 to pi over 2 u du. That's going to be u squared over 2. So that's negative u squared over 2 pi over 4 to pi over 2. I will not substitute yet. So I'm saying method 2, do not sub yet. So I go back and I say, okay, I say -½ u will be, what was u? U was cotangent theta, and so pi over 4 to pi over 2. This -1 over 2 is pulled out, okay, so just to keep it out of the way. Cotangent pi over 2 minus cotangent pi over 4. Go ahead and use your unit circle to come up with the answer for that. Cotangent is the reciprocal of tangent, right? So reciprocal, tangent is sine over cosine, or in other words, y coordinate over the x coordinate. But cotangent would be the flip of it. So it's going to be x coordinate over the y coordinate. So x over y would be a lot easier in this case. So for pi over 2, 90 degrees, x comma y would be, for 90 degrees, 0 comma 1. So that's going to be 0 over 1. And 45 degrees, right? 45 degrees is root 2 over 2 comma root 2 over 2. That's the coordinate. So it's going to be root 2 over 2 x coordinate divided by the y coordinate, which is basically 1. 0 minus 1. So it's negative half times negative 1, which is positive half. The next example is to find integral 0 to pi over 2 2 sine x cosine x over 1 plus cosine sine squared x the whole cubed dx. Okay. Let's look at the denominator. Let's try substituting for the denominator. Let u be 1 plus sine squared x. So that means du be 0 plus 2 sine x cosine x. I know this will happen because with a square we'll do the chain rule. That's what I did, the chain rule. But I know this chain rule is going to be helpful because that's what I have in my numerator. So all is good. It's 2 sine x cosine x dx. So then I do 0 to pi over 2. You know what? I'll try to do method 1 in this one. Okay. So then I'm going to change my limits. So I'm going to use method 1. So somewhere there. Okay. So when x is 0, it means u equals 1 plus sine squared 0. Right? Now sine 0 is 0 itself. So that's going to be 1. When x is pi over 2, 1 plus sine squared pi over 2. So you do sine pi over 2 and square that answer, right? So sine pi over 2 is 1 squared. So 1 plus 1 is 2. So now I'm going to use method 1, which means, let me write the question again. 0 to pi over 2, 2 sine x. Let's fix that. Cosine x dx. All over the whole cubed. So my new limits would be 1 to 2. This is du, right? This whole thing is du. The numerator is du over u cubed. And I can bring the u cubed to the top. That will become u power negative 3. And remember, these limits can be directly applied. These are limits for u. These are transformed limits. So you can use them for u. And just before that, u power negative 2 over negative 2, right? You can rewrite this as u squared, isn't it? That's because I'm going to apply the limits now. I just want it to be meaningful. It's not wrong to have the negative, but it's just so much easier. So I'm going to keep the negative 1 over 2 outside, and it's 1 over u squared, right? So 1 over 2 squared minus 1 over 1 squared. I always like to keep my constant outside, but you'll see that some of the solved examples will keep it together, and then they substitute it. Not a problem. 1 over 4 minus 1. Yeah. So clean all that up. And that's going to be negative 3 over 4. That's going to be positive 3 over 8. Now, if you recall, we discussed about even and odd functions previously. So a quick visit again on that. You know, the figure A is an example of an even function because it's symmetric about the y-axis. So this orange portion and the blue portions are equal and same area. They're both positive areas, so it's enough that you measured one half of them, say from 0 to A, the blue area. If you multiply the blue area by 2, you get the orange and the blue. On the other hand, if you look at B, figure B is an example of an odd function. And so the blue up and the blue down are equal and opposite. The orange up and the orange down are equal and opposite. So if you did 0 to A and you found that area, and if you multiplied it by 2 again because of how you see it, it won't work because they look symmetric, but they're not identical if you were to fold them along the y-axis, because odd functions are symmetric about the origin. So it's as if you folded if this was on a piece of paper, it's as if you folded it along the y-axis once, and the second time you folded it along the x-axis. That's when they will coincide. On the other hand, if they're symmetric about the y-axis, you just fold it once about the y-axis and they coincide. So because of this, the areas are equal and opposite in terms of positive and negative areas, and therefore they will add up to a 0. Okay, that's what this is. And say you had an example like this. Okay, it said evaluate integral negative 2 to 2 x power 4 minus 4x squared plus 6 times dx. Well, you can go ahead and do the regular integration. So you'll just do x power 4 plus 1 over 4 plus 1 minus 4x power 2 plus 1 over 2 plus 1 plus 6x. And then you integrate and apply the limits from negative 2 to 2, top limit minus the bottom limit. You can do that. Or you could test this for symmetry and use one of these rules. So to test for symmetry, the easiest test is, of course, the even test, right? And in fact, when you do the test itself, you can see if it is going to be even or odd or neither. If it's neither, then you really have to go with the regular integration technique. You can't use the symmetry property. So what this says is, if I replaced all the x's with a negative x, I should get back the original function. Right? Now, because these are even powers, this will come back as positive. So x power 4 minus 4 positive x squared plus 6, which is the same as our original function. When you replace the x by a negative x, you got back the original function. So you were able to test that this is even. Because of that, integral negative 2 to 2 x power 4 minus 4x squared plus 6 dx will be the same as 2 times the 0 to 2, 2 times of half the area. I personally feel computationally there's not much of a difference, right? Because you're going to do negative 2, instead you're doing the 0. But then the advantage computationally is that because of the 0, the computation is just easier. Okay. So that's going to be x power 5 over 5 minus 4x cubed over 3 plus 6x, and it goes from 0 to 2. That's 2 times. So 0 to 2, so 2 first, so 2 power 5 over 5 minus 4 times 2 power 3 over 3 plus 6 times 2 minus, now for the 0, and this is where we'll find it easier to compute because of the 0. You know, with practice, we can see that the second part would have been completely 0, so you can kind of skip it eventually, and that is the computational advantage. If you didn't do this, then you'd have substituted for negative 2 in this place, and that would mean that you still have to compute. And if you did all this, you get 232 over 15. That was an example to show how we could use evenness of a function to simplify computation. So I hope you enjoyed this video. I will see you in the next one, and I think we'll be moving to chapter 6. So I'll see you soon.